Hello guys, today we are going to talk about one of the important theorem on the limits, that is the limit of function. Let me write it. The limit of the function limit of the function at a point when it exists is unique. Okay, so here what we are trying to understand is, if at all for any given function the limit exists, okay, it has to be a unique. So therefore we can say in other way that there are no two different limits for a single function. Okay, so to prove this, let us begin with a proof. To prove this, we need the limit definition. Let us consider, suppose we'll start with a contradiction. Like suppose they are given that there is only unique limit, so we will start with the contradiction by saying that suppose there are two limits for a given function. Like suppose the limit of f of x as x is tending to a exists. Okay, it exists and it is not unique. It is not unique. They said it is unique, so we start with it is not unique. So when it is not unique means there should be different limits. Therefore let us take that as limit of f of x as x is tending to a is equal to say L, and limit of f of x as x is tending to a say L dash. So I'm taking L and L dash are two different limits. Where they are not unique means where L is not equal to L dash. Okay, so when I say there are two different limits, so this implies what? When I said L is not equal to L dash means this implies the difference between them is positive. Okay, this is greater than 0 because they are not equal. So if we take, now let me choose, if we take our epsilon as half of say L minus L dash, because as our L minus L dash is greater than 0, our epsilon being greater than 0, this element is greater than 0 and half into the greater than 0 element, the positive element is still greater than 0. So I'm choosing my epsilon should be like this. Okay, so this is like a choice of our epsilon. This is very important. So we're choosing our epsilon to be a half into L minus L dash. All right. So now what we do, then by the definition of our limit, so as we know that limit of f of x as x is tending to say a is equal to L, this implies given epsilon greater than 0. So by the definition of limit, for a given epsilon greater than 0, there exists some delta 1 which is a positive number, such that we know that difference between f of x, the given function, and the limit value, this should be less than epsilon whenever your x value, the 0 is less than x minus a, which is less than delta. So the point x and the difference between the point x and a is less than delta 1. Okay, now again, because we have taken two limits, so again limit of f of x as x is tending to a is equal to L dash. This implies for a given epsilon greater than 0, there exists delta 2 greater than 0. This is with respect to, this delta 2 is with respect to L dash. Okay, so delta 2 greater than 0, such that again by the definition of limit, it says that f of x minus L dash, because L dash is our limit, less than epsilon whenever your 0 is less than modulus of x minus a, which is less than delta 2. Okay, now these are two different values, depends on the L and L dash. Okay, now what we do, let me take our delta as a minimum of delta 1 and delta 2. Okay, so as you have seen that this we have chosen here delta 2 with respect to our L dash, and we have chosen delta 1 with respect to L. Now what we are taking our delta as the minimum of delta 1 and delta 2. All right. So now what we do, we replace this delta by our delta 1 and delta 2 in the above. Okay. So this implies what? This implies our modulus of f of x minus L is less than epsilon. And we also know modulus of f of x minus L dash is less than epsilon when it is true, whenever we have, because we are replacing delta 1 delta 2 by delta, whenever 0 is less than x minus a, which is less than delta. Now you can see in place of delta 1 and delta 2, I am replacing that with the delta value. Okay, so now let us consider L minus L dash. Okay, so this L minus L dash, I will write it as L minus f of x plus f of x minus L dash. There is no harm because I'm adding f of x and I'm subtracting f of x. Okay, now this, by the modulus property, this is less than or equal to modulus of L minus f of x plus modulus of f of x minus L dash. All right. So this one, as you know, this is in the modulus, the entity will be positive. Whatever if you see inside, this entity is positive. So instead of writing as L minus f of x, I can write this as L f of x minus L. Okay. So this is equal to f of x minus L, and this is again as it is f of x minus L dash. But from the above, you know that it is f of x minus L dash is less than epsilon, and you also know that f of x minus L is also less than epsilon. All right. So this we know. So what we do now, by taking that particular value, this is less than, this is epsilon and this is epsilon. Let me write this as 2 epsilon. This is true whenever your 0 is less than x minus a, which is less than delta. Or you started with what? You started with L, if you see, if you started with L minus this value. So L minus L dash is less than, less than, say, L dash minus L, both are one another same, where 0 is less than modulus of x minus a, which is less than delta. So which is what? Which is absurd, because this is like, it is as good as you're getting, this is L minus L dash, and this also is like, that itself is a, that some number is less than itself. That's how actually it looks like, it seems to be. Okay, so that implies what? It looks like absurd. Okay, so here that is what the conclusion, because of our assumption in the beginning. So therefore here you can say that this particular entity, it looks absurd. Okay, or which is, you can, which is logically has no meaning, right? So which is absurd. Okay, therefore our supposition is wrong. Our supposition is wrong. Okay, what is our supposition? We suppose that there are two limits, right? We have supposed that there are two limits, that is, for a given function there are two limits at a given point. So this is our supposition, that is wrong. So our supposition is wrong, hence L is not equal to L dash. So this is our supposition. This is our supposition, right? So L is not equal to L dash. This is our supposition. So hence, which proves that L has to be equal to L dash. L has to be equal to L dash, and which provides that, it also provides that if limit of f of x as x is tending to a, if it exists, it is unique. It is unique. Okay, so this is very, very important, criteria for a given function to have a limit. So if at all we have it's also called as uniqueness of the limits. If at all the limit of a function exists, it has to be unique. So this is how we will be proving this particular result. Okay, so this is all in this video, guys. Maybe in the next video we will discuss the different properties. Okay, and different different examples we will see in the next video. All right, till then, take care, guys.